symbols. You use the right symbols. So if I was to come over here, in what chapter is that in? Not in 4, where they show you the inputs and output ports. Was it 2? Yeah, so inside the PLC, we got the PLC program's got its own symbols. But when I come up here and hook up an input port, that's the one I had up there. Then we draw when we draw the connection of the ports, we use the industry standard symbols for those devices. So this guy is hooked up to port 1. This is an AC input, so we don't have to worry about syncing and sourcing. So they're putting L2 over here, L1 over here. I'm sorry, L1 over here, so L2 would be on the other side, right? So inside my program for this first run, what would it look like? Well, my program, because it's got 120 volts. It could be 120 volts DC, but I doubt it. 120 volt DC would be extremely dangerous. 120 volts AC. So we have several common control voltages that we use in industry. Anybody know what they are? For years it was 120 volts. For years. Then they dropped down to 26 volts. So 26 volts is a very popular control voltage. But it's a range. It's usually like 20 to 30, which is what your input modules actually accept. So when I see 120 volts, that's what our control systems are, so I say 120 volts. But it could be DC. But if it's DC, then we're going to have to specify whether it's what? Syncing or sourcing. Because that would, and it looks like it is DC. Why does it look like it's DC? Yeah, it's got the positive sign on there, thank you. So that means my inputs would be sourcing. If that's positive DC, then my inputs would be sourcing. So my devices would be sourcing, so my input port would have to be what? But let's say this input is turning that light on. So my PLC program would look like this. Okay. And then I'd come over here and do that. And then I'd come over here and I'd draw a coil symbol. Or the OT, it's actually the OTE symbol, right? Syncing, if it depends on what you hook to, what your input device is. So what we got to do is we got to complete a circuit. So positives are looking for negatives, right? So that means if I come over here to get a current flow, so when I come over here and hook this up, if this was a true circuit, now over here, this is plus 120 volts. So what has this got? What's this over here got to be? It's got to be the minus 120, right? Y'all understand that? So what happens is this is the common for my input. So all my inputs are hooking up to plus. So all my input ports are going to be connected to minus. Right? You understand? So and this is true, and this only comes into play on DC. So if you use a common, and when you buy your module, you specify what type of input it is, and that's when you look at this modular PLC. It says that input module says syncing, the output module says sourcing. No, DC runs from negative to positive, and that's what people don't understand. A lot of people think because they got cars on their mind. They got cars on their mind, and cars use a negative for common. It don't matter. It don't matter. Current flows from negative to positive, and that's why one of the questions was crazy. It says current flows from L1 to L2. That's false. It could be true, but it could also be false. If it's AC has no polarity. Or L1 and L2 negative could be on the left and positive could be on the right, or what? Positively on, so it's up to the company to decide what they run. And so and if you buy the wrong input module, that means your input devices won't work. Because you got a syncing input device hooked up to a syncing port, right? You understand? So you don't have any current flow between your device and the port itself. So you won't hear me say current flow, you'll hear me say signal flow. So signal flow is from left to right. So our inputs are on the what? Left. Our outputs are on the right. So the signals are going to flow what? From left to right. So that's a true statement. The same current flows from left to right. When that was on the test, we must have skipped that one. I'm almost sure it was. So current flows from left to right. So what I would do is I would assign this. So what I'd have to do is I'd have to know the module number. This don't tell me the module. All it does is tell me the bit on that module, right? So we put that on module 2. We put that on module, 1. We put that on module 2. Then if I was going to turn on this light, then over here I would put what? I would put N, colon. Then I would put the module number, right? No, I just made up something. It looks kind of like a fixed PLC because it don't have 16s, but it don't make any difference. If it's a fixed PLC, your module address is going to be what? 0 for both your inputs and outputs. If you're in a modular PLC, so if you get on one of the 504s, you're going to have to, when you create your program, you're going to have to specify those input and output modules. Now it's no big deal. You're going to have to specify the size of the rack. So how many slots do we have? We got 7. We're going to say, okay, it's a 7-slot rack, and then numbers will pop down in there. It says 0 through 6. And you don't have to put the input module right beside. You could put the input module out at slot 4, right? You understand? It's just that when you write your program, you would address it at slot 4. So we can move these around. There's nothing in the rule book that says the inputs have got to go in slot 1. It's up to you, right? Understand that? Huh? Yeah, make sure you address it right. And don't move the modules. Because when you write your program, you specify an address of an input bit, right? You understand? When you go in there and you shift it around, none of your programs are going to run anymore. It's going to say burp. So this would be the PLC program right here. Out, then we'd say 2/ what did I say? We're turning on that light. 0. Now we got the common hooked up to the lights. We got positive hooked up over here. Common's over here, so they've established the common. So these outputs are going to be sourcing, right? You understand? So this would be my PLC program right here. So when I hit this button, there's the truth. That is the symbol that says I have a switch hooked up there. So that's what I'm trying to get across. When you draw your connections to your modules, you're supposed to use the industry standard for these different devices. So what's the top one? Normally open, single post, single throw. Anybody know what that means?
It has something to do with L1 and L2, doesn't it?
Nothing to do with L1. Throws are the number of positions. Poles are the number of switches. So if you look at chapter 4, so y'all open up chapter 4. And the first switches, the first symbols they give us. What's the first symbols they give us?
The very first one on 68?
Yeah, but I'm on page 69. Has the new books come in, guys? Anybody went down and checked? Any word on when they'll come in? So what I'm going to do, what I'm going to try to do this afternoon is I'm going to try to upload the PowerPoints that actually come with the book. So we're in chapter 4. And you can see in the PowerPoints that come with the book, they're more in line with the book. Nancy's PowerPoints are good. They can. I'm gonna put all of them up.
Thank you.
And I have up to lab 6 ran off for the people that don't have their lab book. 6 is when we go down there, so I'm not gonna give that off right now. So this is what I'll put up there, and this is the PowerPoint that actually go with the book. And so it's got the contact. This is the one I'm looking at right here. Yeah. Course content, and then lecture slides.
All right. I'm still back on the conversation. Our sources input is going to be 5.
It depends. So what you do when you hook up your if it's a DC PLC, you buy it. So for some reason, Siemens PLCs are normally syncing input and sourcing output, which is used all over the place. Allen Bradley PLCs, since they're used all over the world, they give us the ability to select what we want. But they don't give you the ability to select everything. So, hold on, let me pass.
I'm not real cool on something myself.
Where's the 1,000? Where's the 1,000? The problem is when you buy a DC sensor, when you buy a DC sensor, they got to generate the output somehow. So we have 2 devices. We have several devices that we use as a switch, but the most often used device is something called a bipolar junction transistor, because these guys switch it real fast and they can handle a pretty good deal of current. We have 2 versions of the bipolar junction transistor called an NPN transistor and a PNP. Well, when they designate syncing and sourcing sensors, sometimes they say it's an NPN or PNP sensor. Well, an NPN sensor is a syncing sensor. A PNP is a sourcing sensor. So that's all you need to know.
NPN.
Well, it is. You have to worry about the negative positive, because that is if it's a sourcing sensor. So what we've got is we've got this side. There's no when we hook up something to an input port. Normally we use one thing per port, right? You understand that? So what happens is you come over here and you have all these inputs, and these inputs are going to have a common connection spot. So the problem is we get used to saying common is the return. So what I've got is I'm going to come over here and I'm just going to come over here and connect all these. I'm just going to put push buttons, and I'm connecting these down L1. Now a common is just a common connection spot. So if this right here is plus, then what's the common for the switches? Plus. Well, what's this thing looking for?
Negative.
It's looking for a negative. We got to complete the circuit. So my input module, so this would be, if this is input 0, then this side of the PLC is going to be connected to minus. So now I have now this is using the minus as so all my ports are using minus. So these guys are what? So that's why we're saying, if I'm using a sourcing input, if I'm using a sourcing device, I've got to hook it up to a syncing input. So it means on this guy right here, it's a syncing input. So if I bought a DC sensor, I would buy PNP sensors, because PNP sensors are sourcing sensors, right? Y'all understand that? PNP.
Is that like positive and negative?
No, well, sort of. Yeah, but you can't really use it. You can use it for the base to emitter, but you can't use it for lead we call a collector. PNP stands for the majority carriers inside the region. So P means the majority carriers are the absence of electron. So if I take an electron, so we got electrons and they're all balanced, right? So if I come over here and I pull one of the electrons out of then it's an unbalanced electron. So if I pull an electron out, then the atom would carry a positive charge, and those are P's. If I pull an electron out, if I put an extra electron into the crystal, then I end up with more electrons and I got protons, and we call that an N. Now then we have something called forward bias, and that's the polarities we put on a bipolar transistor to make it work. So on a PNP, if you use polarities, you'd be wrong, because what I would do, I'm sorry, this is an NPN. The way I would bias this is I would come over here and make this negative, I'd make this positive, and I'd make that more positive. So I'm putting a positive on that top leg. So you can't say it's the polarity that you put on there. So the PNP sensor, this right here is that's what's connected to P, and that's your output right there. So this is your current valve. So a transistor is a current valve. That's all it is. Everybody know how a water valve works. What can you do with that water valve? Yeah, well, or you can turn it a little bit on, a little bit off. So we can operate this, and we can operate it. So in amplifiers, we operate it as in between. If we're going to use a switch, we either turn it all the way what? On or off. And so we call it saturation and cutoff. So that's what we do. We hook up, and so notice here, we hook this, I'm sorry, and then the NPN, and this is how this is what we keep up with them, is that arrow right there. We look at this arrow right there, and this is not pointing in, right? We look at this arrow right here, and it's what? Pointing in, and that's the symbol. But you don't need to know that. All you need to know in this class is that if they don't specify it's a sinking sensor and they don't specify it's a sourcing sensor, an NPN is a sinking sensor and a PNP is a sourcing sensor. Yeah, sorry. Yeah. That's all you need to know in this class. Just if you needed to buy a sensor, right? That's DC. That's DC. Yeah, AC, we don't care. AC has no polarity. Right, you understand. Like I said, Alabama Power is switching polarities 120 times every second. So that means this sucker switches polarities every 8.333 or 0.0083333, and it goes on for every milliseconds. That sucker switches polarity. It's a lot of switches. Hertz would be it's 60 hertz, but you have two alternations. So for every cycle, you have a positive and negative alternation, or we call it a negative voltage. And so you actually have two switches per cycle. So if you got, so if I'm buying a sensor and I've got a sinking sensor and it specifies I need to buy a so if it's a sinking input, then I'm going to use a PNP sensor, right? You understand that? Sinking input's got to have, sinking input's got to have a sourcing sensor. Push buttons, it don't make any difference, PNP or NPN, because they're push buttons. But we establish a common. So we call this, if it's got a positive common, we say it's sourcing. So if your switches have, or your input devices have your true physical input devices, not your program. If they are connected to the positive, then these are sourcing devices. And it means your input's got to be a sinking, right? Everybody understand that? Well, good. So here's the name of these switches. We have what we call poles and probes.
Is that what the
You already
switch
added.
comes from?
You already added that.
Big pole.
No.
Oh, no. And that's what I've said. I'm gonna take the ones right out of the book. The ones that Nancy has everything that's in the book, but she just don't do it in quite the order, which is really good because it makes you do move things around. This goes in the order of the book. These are the ones that was actually supplied by Goodhart Wilson, the publisher of the book. So what I'm gonna do is I'm gonna put both of them in. And I'll put it, there'll be a folder up there called Goodart Wilson. I'll call the other one Nancy.
I was looking here, I was also kind of going along with the lab. And I noticed that every time you got a closed switch compared to open switch, they usually put the line of the switch on the opposite side of the contact.
Not on toggle switches. On toggle switches, whether it's normally open or normally closed, we still put it on the top. But notice what they do on the toggle switch. So you normally open, rest up above it, you normally close above here and rest on the little terminal. These are for switches. So what's the light switch?
This book is opposite.
No, I'm not
On
gonna
the
read it.
hands down?
If your book, it says that it's wrong.
I'm right underneath push buttons and switches at push 1, 2.
Yeah, but we're identifying whether it's normally open or normally closed.
Yeah, I'm like that. It looks just like what you got there, but on the closed side, it's got the line underneath the contact.
That's not a switch. Well, it's not. It might be a limit switch.
Well, it says normally closed, switch held open.
Well,
Yeah.
That's
the
different.
one that's hanging down. The one right above it.
Yeah.
It's weird that it's still. I'm not talking about hanging. I'm talking about that they still are putting it on the opposite side. And that's why when I'm going through on my lab, there's some of these only have the open version in the book. So does it matter that much when drawing in the picture in the lab?
Yeah, I see.
That line needs to be on one side or the other.
See it on, that's the book. And then over here is what you're talking about, the limit switches. So is it incorrect?
This normally on a standard switch, we draw everything above the line. But when we get to a sensor like a limit switch, where's the pictures at?
You don't have it for some reason.
Count off for points, having a line. You know, the closed switch is obviously closed switch, but it matters whether or not that line is above.
Well, on a limit switch, it would. Y'all know what a limit switch is?
It's still limited.
It should look like this. That, but you don't have it.
So this is the limit. This is a high current, high capacity. When we get into PLCs, guys, very little current required by your input, so you'll run into little old tiny, these micro limit switches. I didn't bring my camera, but I'll use it. Can't read it. I don't have it. Don't like that either, does it? I might not be able to record this. I can pass it around. Okay, we go. So this is a heavy duty, or what we call a pilot to the limit switch. So we usually have a cover right here, and then the connection to it runs up into here. And then it has an operator. We can get different operators for the limit switch. And then when something comes along and hits this, you can hear it actually click. So it's got a little unit in there. It's kind of a plateau that it won't switch, and as soon as it clears that plateau, it snaps. Because what you want to do on a switch that's covering current is you don't want it to close real slow, right? So most of these things are snapping. And that's why we call light switches. What does most electricians call light switches? Anybody know? They call them snap switches. So you give them some snap switches, because that's, this only operates in one way. Some of them operate with another. These are the actual contacts, you can see in here. I don't know if it's got, looks like it's got a set of normally open and normally closed contacts. You can actually see the wires where I hooked this up. This got the name because this literally was used to detect limits. So when something hit a limit, it would reverse it or something like that. Now we use them to detect position. We use them to count things. You can get a little old small one that's got a big wiper out. These things come flying by and he's just sitting there flying up there. But it got its name limit switch. It's a type of proximity switch. A proximity switch tells us when something's at a certain point. But limit switches have been around so long, we don't call them proximity switches. We call them limit switches. And then we got what we call proximity switches, which are usually your solid state switches, non-contact. So a limit switch is an electromechanical device, and it is a contact sensor. So what does that mean? It's got to make physical contact with the device. So we got all kinds of things on this thing right here. Your operator could break. I've seen people mount the things wrong. They'll go out there. I've seen them weld. They lost screws, they'll weld them up. When they don't put them in the right position, they'll put them up too high, and it comes along, and the operator just tears them up. The cam just tears the operator off. I've seen them mounted upside down. Well, when we draw the limit switch, so this is where we start drawing. This is where we start using that second symbol. So the symbol for a limit switch is we basically come over here and we draw it like this, no matter what the operator is. So what we do is we draw this. This would be normally open, and then I put this little V right there. That's the symbol for a limit switch. And so this would be a normally open. Now this is where that comes into play. So on our control devices, if I draw it below it, then this right here is a what? I'm sorry, that's not right.
Let's say in the book it's got normally open.
Yeah, I'm wrong.
Down and east.
Yeah, so this right here would be a what? Okay, so this is a normally open. This is a normally closed.
See, that's what I was asking with the opposite with the contact.
Now, for all your limit switches, we have some solid state limit switches, and sometimes they will use this symbol, even though they're not supposed to. We have another symbol for solid state sensors, which I'll show y'all in a minute. I don't know if the book covers it or not, but I'll show y'all some actual prints. If I came over and did this, what we do is we look and see what gravity's trying to do with the switch. So what's gravity trying to do with the switch? No, look, what's gravity trying to do? It's trying to open it. So this would be a normally open held closed. Held closed. It's held closed. If I came over and did this, what's gravity trying to do? It's trying to close it. So it must be what? Held, must normally closed, held open. So notice this guy right here, this is normally open. What's gravity trying to do? It's trying to open it. Well, it's open. What's gravity trying to do with this one? It's trying to close it, and it's closed. So this would be normally open. This would be normally closed. I look at this one. What's gravity trying to do? It's trying to close it. So it's got to be a normally closed, held open. Now what we do on these is we draw these symbols like the machine is when it's at rest or when it's at reset. So that means if I've got a big carriage out there and I'm trying to sense where it's left and right, and we always park it on the left, and it's got a normally open switch, then when we draw our diagram, it would be a normally open, held closed, right? That makes sense. So that's why we have these different symbols, so we can put what that limit switch is when the equipment is what? At rest. And then I would come up here and do what, guys? I would hook this up to a plus or a minus, and then I would take over this and hook it up to one of my inputs. And then I would write a program to do what? To do what I want to do because of that input. Yeah, right? Y'all see the single pole, double throw, single pole, all those different things. Do y'all understand those?
I imagine that's what I mean by throw. That's what they got the term.
Number of poles is the number of switches. The number of throws is the number of conditions or positions that switch can we can put it into to control the circuit. Dotted lines means they're mechanically connected together.
Okay, the number of poles is, say that again, please?
The number of switches or the number of contacts. So if I bought a relay, so that relay that I passed around is a 2-pole relay.
And then throw?
No, they're both. So we would call this is called a 2-pole single throw relay.
2 poles.
There's 2 contacts in here. So it's 2 switches. And each one of them's only got one position. We can either close it or we can open it, right? Now if I was to come over here and connect these together, then they're going to act like a single pole double throw. So we can make a relay.
Contact would be pole.
The number of switches, or the number of, would be the number of poles. The number of positions that switch can be put in that controls a circuit, right? You understand? Is the number of what? Throws. So if I come over and do this, what's that? Single pole, single throw. Because the open is not putting current to a circuit. If I came over here and did this, single pole, double throw. One switch, we can control 2 circuits. If I came over here and did this, I'm going to come down here and do this, and then I'm going to put this little dashed line. It means they're mechanically connected. What is this? Double pole, single throw. Yeah, because each switch has only got one position. Okay, understand? Now, if I come over and did this, and this is pretty much, well, the limit, guys. If I came over and did this, and then I come over and did this, and then I put the little dash line, then that would be double pole, got 2 switches, and then each switches can control 2 circuits. So this would be a double pole, double throw. Now notice in contacts, it depends on how the contacts are wired. So if I have 2 contacts right there, then this would be a what? Double pole, single throw. Because the contacts are only one way. We do have some relays that are wired like this. They come over here, and they usually draw them as switches, guys. So that's this guy. It's a control relay. That's this guy right here. You look at the diagram on the side. Right here. So the switches are mechanically connected inside. So this would be a single throw, double throw. This would be 1, 2, 3. That would be 4 pole, double throw. It works just like a switch would, where one of them's open and one of them's closed. Here's the diagram for it. You can look for it. Sometimes they put it on the top. It's very confusing on the top. So what you're looking at there is you're looking at a triple pole, a 3-pole, double throw. I could show you that.
I think make it easier.
No.
By the pole, the side of the switch that's connected where it pivots. That would be
the number of poles
pole. And the switch on the other side
that you're actually switching.
from.
How many directions can it switch and control a different circuit? Yeah. And we've got these push buttons right here. We got a couple of double pole, double throw. Now, a double pole, double throw is going to require one normally open and one normally closed. So these push button stations are here. Here's the diagram. So this is the double pole, single throw. This is double pole, single throw. And this is the single pole, single throw, normally closed. Double pole, a double throw, you can't say normally closed and normally open because when one of them's closed, the other one's going to be open. If you switch the position of the poles, then the contact depends on how you. This is the push button station. The two push buttons on the right that's labeled stop and start. The one's labeled start is a single pole, single throw, normally closed. The one labeled reverse is a double pole, single throw, normally closed. It depends on which way you hook it up. So it depends on which way you hook it up. Does that make sense? Then the forward button is a double pole, single throw. But I can wire them together and make them appear to be a double single pole, double throw. If you put a jumper between the left side. This is a list in the book. I'm sorry, I don't know. About what? Single break, double break is in most of our switches and most of our relays. The problem we have with single break, so this would be single break, is that if this contact right here gets welded, and this happens all the time, then we can't open that section. But what we do with a single break contact is the contacts literally float. You can come up here and take something and you can push this. So this is a double break contact. So this right here literally floats. I'm pushing it with a pin. I'll sit there and put it on there. So what we mean is we break both sides. So we just don't break one side, we break both sides. So just about all our push buttons are double break push buttons. And most of our relays are double break relays. Not all of them, most of them. So I'm going to take my pin, and here's the contact right here, and I'm going to take my pin, I'm going to do the normally open, or the normally closed, and can you see it just floats? So what happens is that if one side gets stuck, when it breaks, it's going to literally, this side's going to fall down, and what's it going to do? It's going to tear that other side loose. So the advantage of double break contacts or double break push buttons is that they're more likely to break a circuit if one of the contacts get welded together. And you got a lot of heat. When you create an electrical arc is around 32,000 degrees, hotter than the sun. So if you don't break these things extremely fast, then what's going to happen? Well, those contacts are literally going to weld together. And we have that happen. So that's why these switches snap. We have snap switches, right? So when you hit that limit switch, what did it do? You can move it as slow as you wanted to, and it wouldn't switch until it went over that plateau, and then it pops. So what do we want to do? We want these contacts to break extremely fast and close extremely fast. The problem with a single break contact is that it's more likely to do what? Well, double break contacts are more likely to break through if one side gets what? If it gets welded, if we get an arc in there and it welds it. When it drops, it's going to do what? This side's going to drop down first. It's going to do what to the other side? Pull on it in an angle, not straight down. It's actually going to pull it on an angle. So when you pull stuff apart, you don't grab it and do like this. What do you usually do? You usually start on one side and what? And pull it. And so that's what double break means. Any more questions? Because I got plenty of answers. In fact, I got more answers than I need to have. Don't I? But what you got, this only comes into play in this class, and this is what you're going to have to do. When you start looking at your more advanced labs, what you're gonna have to start doing is you're gonna have to start drawing the hookup for the input ports. Now, what's nice about us is that we've only got certain switches, right? But we're gonna simulate stuff. So when you're in the lab and it says, when this limit switch goes, well, what we're gonna do is we're gonna simulate the limit switch with what? No, we're gonna simulate it with this switch. A limit switch is that big old thing that I passed around, but we don't see any limit switches in here, right? When you take motor controls, you're gonna hook up limit switches, you're gonna hook up timers, you're gonna hook up all kinds of stuff. No, this is physical. Once it gets into the PLC, it's no longer physical. But what we're doing is we're going to use, instead of saying simulate, we're using a switch to act like a limit switch. We're going to use a switch to act like a temperature sensor. We're going to use a switch to act like a inductive sensor. But what you need to do when you draw your connection, you need to draw the right symbol. Don't draw the symbol of what you're using. Draw the symbol of what the PLC says that we are acting like, right? So what does a temperature sensor do? A digital sensor or discrete sensor. What is a digital? And it kicks, or we usually set a range. So we set a range. We have an upper and lower range. So usually we have a deadband. And we got temperature sensors. We got all these sensors. We got temperature sensors. We got optical sensors. And what I'll try to do, I'll try to come in here next class and literally wire some of these things up for you and actually see the actual sensors work. But we don't hook up the sensors, but we're going to. I'm trying to say simulate, but I won't get in trouble. You're going to use a switch to take the place of that, right? Y'all understand that? Because that's all these sensors do. They might do it electronically, but that's all they do, right? These discrete sensors, all they do is either they turn on or turn off when whatever they're designed to detect. And we'll show y'all some little things on that next class. Huh? Yeah, so what you're going to have to do is you're going to have to do kind of like what they did in the other lab. This guy don't let me bring up anything. He's got priority over it. So this is what you're going to do. Yeah. So you're going to have to draw it out using the symbols that represents what you want to do. So that's a switch, normally open switch, that's a momentary contact, normally open contact. You gotta look real close, there is a break. The normally closed push button is going to be below the dot. So what is this? Oh, it's a thermostat. I don't think any are allowed, I don't know, some are allowed thermostat. This is what they say we're going to use for motors. In motor controls, we modify this symbol a little bit. We don't put this little list on it. That's really good because you can really tell it's a motor. These are symbols for what? Light. What do you think of G, R, and W? Green, red, and white. But you don't have to call them green, red, and white. You can call them different names. So if I look at the switches, if I look at the lights on this guy. This is labeled start, this is labeled start. And this is labeled stop, and this is labeled start. Right? So, but the start is red, the stop is red, and the start is green. And that's industry standard color for that. Even though I think it could probably be backwards. It changes. So odds are you're right, they're not going to be called red, green, blue, they're going to be called something else. And it'll define that in your activity when you start building these things. What would be nice is give your lights the same name that you give the symbol, right? So you put that OTE symbol out there, whatever name it tells you to give that, go ahead and give your license. Well, that's not true. You're not gonna, oh yeah, that's good. So just about every lab, if I know right, is it's gonna tell you what he wants to do. It's gonna have you figure out how you want to connect the thing up. I think all ours are gonna be sourcing inputs, are gonna be sourcing inputs and syncing outputs. I don't think they do this side for you. You don't have to run individual lines, guys. You can do one. You can bring it all the way over here and bring it over. That's up to you. That's just the way they do it here. So what we'll talk about next class is we'll look at some of our proximity sensors. Push buttons. We got push buttons all over the place here, guys. Proximity sensors we'll look at is some photoelectric sensors. We don't have a capacitive sensor over here. We do have capacitive sensors over in the over on the Amtrol line and also the Festo line. We do have an optical sensor, which is pretty neat. But I'll try to remember to bring a reed switch over here. Radar sensors, ultrasonic sensors, Hall effect sensors. Y'all heard of those terms before? If you got a burglar alarm in your house and you got a little old tiny switch up on the window, that's a Hall effect. Yeah, Hall effect. No, it's not the motion sensor. It's the one that detects if the door is open and closed. They in our church, they put up all these motion detectors over there, and there was a dead spot. Somebody could come in one of the doors and get up in our audio booth and steal everything we had, and that thing would have never went off. But if they'd have put like noise detectors or glass break detectors and plus those switches on the doors, then it would have been a lot safer. Yeah, I used to sneak in there all the time because I had a key. I was the audio visual guy. So any questions? We skipped over our last break, so we're fixing to cut out. But y'all have any questions on what we've done so far? What am I going to do?
Put the test up.
I'm going to put the test up there. Yes.
PowerPoint.
Yeah, and let me give, for those that hadn't got your lab book, let me give y'all some of these labs.
Speaking of labs, there was that first lab we were working on the other day. We need a blank lab sheet to go with that. I don't think we got one. Did you get one? Did y'all get one? I didn't get one. I got one handed out. Yeah, did y'all get one? I didn't get one. When do you want to turn in?
You didn't get a lab sheet? That was the first thing you told me.
I got the one that you had where it said Bill Hall.
Yeah, but you're supposed to tell me you can sign them. Y'all don't forget the.
Is there a due date for these labs or what?
Do what you can do during the weekend. See what, there might be some stuff you can't do without being here. But the 3-1, everybody should do that. That's the numbering system. I've lost it. No, this is pink. It don't matter to you, but it matters to me. No, I'm joking. I've lost my pen. It's a great pen. Yeah, there will be a due date on the test. How long y'all want to do it? Can't let y'all have forever. Sunday night?
Yeah.
The wiring diagram.
Does anybody want to do a study group?
Not this one?
Anybody want to do a study group? Yeah. Before the test, or Monday, or
During the test.
It's in here somewhere. Is this the right one?
You guys, if anybody wants to be in a study group, I'm gonna put just a piece of paper right here. You can put your name and phone number, and I'll text. I mostly text. Some of us want to get together, so just put your name and number, and if I can text, that's great. If you don't do texting, just put email on there, and then I'll contact you that way.
No, this is it.
Okay, yeah, that's cool. Just whatever you go by.
Second sourcing. There we go. That slide right there.
I see the inputs. So the inputs is whatever you assign out. But these might not be yours. Assigned out.
Yeah, you assign the out. So what you do in your ladder diagram is you say, I'm going to use this input to control this device. And we could come up here and, I could do more than one input. So on my program, I could come over here and I could say, I could come over here and do this. And I could say, I'm not going to do all the addresses. I'm going to say input 0. Then I could come out by it and I could say what? I could say input 1. I mean, you can do that, no problem at all. And then you come over here and eventually, right now, we're going to assign it to an output port. So which one do you want to do? Do you want to turn on the motor? Do you want to ring a bell? So it depends on what you do. Do I want this to turn on the green light, the red, white? So let's say I wanted to run motor 1. Then I would come over here and my output would be output 3. So now I'd have to do both these buttons. I'd have to do the switch plus the button. And then that would energize that output. That would turn this guy here on right here and come over here and this little motor would run. That must be a little motor.
Alright. Appreciate it, y'all.
It's syncing.
Which one's syncing? Sourcing switches, syncing input. Syncing output, sourcing module, right? Makes sense? So this is syncing. And this right here would be sourcing. And why is this syncing? Because this right here is plus. So there's your plus. So then this guy somewhere, somehow is going to have to be referenced to minus. And since this guy here is this is plus, this has got to be minus, right? So if all these guys are references to minus, then my modules have got to be referenced to plus, right? So we're saying sourcing input devices have to hook to a syncing input, and then syncing output devices hook to a sourcing input, which is what we have here.
I'm getting it.
We're gonna try to do it Monday. I mean Tuesday. As many as you can do, right? Huh? Yeah, did you get that number?
That's because you don't want us to turn our laps in.
If you got some finished, yes. If you don't have it finished, no.
You want us to stay with these two together?
According to procedure.